So we will start with for a beam one. Here if you see, this is a compact and non-compact and slender sections. The flexural capacity of this steel beam that depends on the slenderness ratio of its compression flange and web. Okay, this determines how effectively the beam can resist bending moment without buckling. So first, what you have to do, you have to first check the beam slenderness ratio for the compression flange and web also, because depends on that the flexural capacity of the beam, it will vary. So this determines how effectively the beam can resist bending. That means like how much bending moment it can resist. That depends on this slenderness ratio without buckling. So based on these ratios, the beam can section can be classified as compact, non-compact, and slender. So there are three type of classification for these beams. One, if you take it as a compact section, that's the one that can fully develop its plastic moment. So you have to understand, like, if the compact section beam is a compact section, then it can develop its full plastic moment before local buckling of the flange or web occurs. Assuming the beam is laterally braced, a section is classified as compact if its slenderness ratios are below certain limits, allowing the beam to reach its maximum bending capacity without any premature local buckling. So that means, like, when you have a compact section, that time only the beam can reach its maximum bending capacity without any premature local buckling. So before local buckling happens, it will, like, local buckling, it will not happen because the beam section is compact. That's why it can go up to its maximum bending capacity. That's the plastic moment. That means it can fully develop its plastic moment. So we need to see the slenderness ratio for the flange and slenderness ratio for the web. So there is a how you are going to calculate the slenderness ratio for the flange. So this is our beam, I beam. Okay, so you know BF is nothing but the beam flange width. That's the beam. F is flange, beam flange width. TF is nothing but thickness of this web. This is the thickness of web. Thickness of web. So by using this ratio of B by 2 TF, B by 2 TF, you can find out the slenderness ratio of the flange. So B is the flange width, TF is the flange thickness. A section is considered compact if the flange slenderness ratio is less than the limiting value. So you can calculate this value B by 2 TF, but it should be less than its limiting value. So we need to know what's the limiting value. So limiting value is calculated using this formula. So limiting value depends on the E and Fy. E and Fy. E, you know, Young's modulus, and Fy is the yield stress of the steel. So E is Young's modulus, Fy is the yield stress. For the web, the slenderness ratio is defined as H by Tw. You know the height of the beam, clear height between the flanges. H is not the overall height; it's a clear height between the flanges. That's the height H, clear height between the flanges, and Tw is the web thickness. So this section is considered compact if the web slenderness ratio is less than its limiting value. We have limit. If we are within the limit, then this can be considered as a compact section. If we are going out of that limit, then it's not compact section. When the section is compact, it can develop plastic moment. I told you that it can develop fully develop its plastic moment if the section is compact and laterally braced properly, assuming it's laterally braced. Okay, so the plastic moment means, like, nominal strength we can calculate Mn equal to MP. MP is nothing but the plastic moment, and Fy, you know, Fy is the yield stress of the beam, and Zx is the plastic section modulus of the beam. The plastic section modulus of the beam depends on the sectional properties that you can take it from the AIC manual, or you can calculate manually also. The beam thus can carry the full plastic moment without premature buckling of the flange or web. So now you can understand that the beam, it will not go premature buckling. It will not be subject to premature buckling of the flange or web. Before that, like, without that buckling, it can carry the full plastic moment. The next one we can see non-compact section. Non-compact section is the one where local buckling of flange or web may occur before the full plastic moment is reached. So there is a difference between compact and non-compact. In the compact section, there will not be any local buckling, premature local buckling before it reaches the full plastic moment. But in case of non-compact section, the section can go like where one local buckling of flange or web may occur before the full plastic moment is reached. But the section still can develop a nominal flexural strength (MN) in the range between elastic moment and plastic moment. So it will be in between the elastic and plastic moment to that range. So in this case, the section can reach some but not all of its plastic capacity. So if it is a plastic capacity is MP, it can reach to some percentage of it, not the full plastic capacity it will not reach because it's a non-compact section. So criteria for determining non-compactness in the flange is this is the one, like it should be more than this and less than 1 into square root of E by Fy. RF is the limiting slenderness parameter for a non-compact. Lambda RF is the limiting slenderness parameter for the non-compact flange. Web also we have the criteria for non-compactness. Lambda RW is the limiting slenderness parameter for the non-compact web. That's 5.7 into square root of E by Fy. For a section with compact web and non-compact flange, assuming adequate lateral bracing, the nominal flexure strength can be calculated using this equation. So Mn equal to MP. So in this MP, some portion it's getting deducted. So MP into 0.757 Fy into Sx minus lambda PF, lambda RF minus lambda PF. So lambda we know the flange slenderness parameter. So plastic moment of capacity, Sx is the elastic section modulus about the axis. Now let's see the slender section. Slender section is one where the flange or web is so thin. If it is very thin, the slenderness ratio is very high. That local buckling occurs before the material reaches its yield stress. Before the material reaches its yield stress, before it reaches yield value, the local buckling is occurring. A section is classified as slender if the slenderness ratio exceeds its limits of non-compact section. We know the limit for non-compact flange or non-compact web that we have seen lambda RF and lambda RW. If the slenderness, if the flange, for the flange, if the non-compactness goes more than this, then it becomes a slender section. When the section is slender, nominal flexure strength is calculated differently and reduced based on the slenderness ratio of the flanges and web. For slender sections, the nominal flexure strength is given as 0.9 times E Kc and Sx lambda squared. Kc is based on the slenderness ratio. Here you can see 4 by h TW into 0.5, where 0.35 to Kc will be in the range of 0.35 to 0.76. Note there are no roll shapes with slender flanges or webs under normal design conditions. So if you are going for roll shapes, there will not be any slender sections are not typically encountered in practice. This is one example. You see the modulus of elasticity and yield value. Beam section properties it's given. And first step, you have to calculate the slenderness ratio for the flange. Slenderness ratio for the flange is calculated using this formula lambda PF equal to BF by 2TF. BF we know 12 inch and 2 times thickness of flange is 0.5, so it becomes lambda becomes 12. Plugging in these values, we get lambda PF as 12. So next step 2, calculate the slenderness ratio of the web. Slenderness ratio of the web is calculated using the formula. So web slenderness is calculated using the formula lambda PW equal to h by dw. So once plugging in these values, we get lambda PW is 72. Compare with the limiting slenderness ratios. The limiting slenderness ratios for compact sections based on AIC 360 specifications are given by, for flange, that's the lambda PF is this value, and substitute this E and Fy, then we get the value of 9.15. So the limiting slenderness ratio for the flange is 9.15. For web also, lambda PW, once we plug in these values, substitute E and Fy, then we get lambda PW, that's 90.5. The limiting slenderness ratio for the web is 90.5. Compare the slenderness ratio to the limits. So for flange, the slenderness ratio is 12, which is greater than the limiting value. So this means flange is not compact. For the web, slenderness ratio is 72, which is less than the limiting value. This means web is compact. So flange non-compact and web is compact. This is how the beam section, we can see beam section is in this example is classified as not compact. Since flange is not compact, even the web is compact. Here we can see for non-compact section we cannot use the full plastic moment capacity as we would for the compact section. The nominal flux strength will need to account for the reduced strength due to the non-compact section. Typically this would involve adjusting the design strength by applying a reduction factor. So we will see it in this next example. So this example shows how the slenderness ratios are used to classify the section and determine whether section is fully efficient, compact, or needs further considerations, non-compact or slender. Let's see another example. So here you can see, let's go through an example for each type like compact, non-compact, slender. We will calculate the nominal flexural strength and the design flexural strength also using LRFT as well as AST. So compact section example, determine the flexural strength, allowable strength. So we have to calculate first the design flexural strength and allowable flexural strength for this particular beam W12 by 40 with the FY is 50. So we know the beam flange width, flange thickness, clear height, web thickness, yield stress, modulus of velocity, elastic section modulus, plastic section modulus. For all for this W12 by 40 beam we can get it. So first step is calculate slenderness ratio parameters. Calculate for the flange, substitute the values, you will get 8.64. For the web also you can calculate. Once you put this h by dw value, you get this value. Then compare the slenderness parameters with the limiting values. For the flange, we know the limiting slenderness is for compact flange. This is the value. Plugging in the values, you get 8.14. Since lambda pf 8.64 is more than this, flange is compact. The limiting value is more than the actual one, so flange is compact. And web also, if you see the limiting slenderness for the compact web is lambda pw, it's 14.64. Actually the lambda slenderness limiting value is 29.25, is greater than the 14.64. So web is compact. So one calculate the nominal flexural strength, MP. Actually this is should be less. The actual value is greater than the limit, means this is not compact, this is non-compact. The same way here also lambda pf is greater than the limiting value. Limiting value is 8.64. If it is more than that, this is not compact, this is not compact. We cannot use this one. This is only if the section is fully compact, then we can use the full plastic moment capacity.